Hi, my name's Dan. I'm a grad student in Illinois. My advisor is Professor Gul Aga, and today I'll be talking about a garbage collection algorithm for actor systems based on what's called termination detection. It's designed to scale to large clusters without significantly affecting latency. So actor systems are built using the actor model of concurrency, where these lightweight stateful processes called actors communicate with each other by sending asynchronous messages. The model is pretty popular for building low latency distributed systems like databases and chat applications. And these systems are usually run on a cluster of servers where each server can host millions of actors. So right now, the most popular frameworks for distributed actor systems are probably Erlang, Elixir, Akka, and Orleans. And they all have automatic garbage collection for passive data like records and objects. But interestingly enough, none of them have GC for the actors themselves. So programmers have to garbage collect actors manually, which means, as you can imagine, it's a significant source of bugs. The issue is that ordinary GC techniques for a language like Java don't work for actors. And although plenty of actor GC systems have been proposed, I would argue that none of them scale well enough on clusters to make them a viable choice. I'll talk more about that a bit later, but first we should review how actors work and introduce some terminology. So as you can see in the legend here, we denote actors as circles and messages as dashed arrows. And here we have an actor with an undelivered message M. So initially an actor is idle, meaning it's waiting for a message. Once an idle actor receives a message, it becomes busy, denoted by this orange square. And a busy actor can then do a number of actions, for example, spawning new actors. Notice that this gives the parent a reference to the child, which allows it to send asynchronous messages to that child. And these messages can contain ordinary data like this hello text, but they can also contain references. Here the parent's sending B a reference to A and B receives it. So note that a reference is just an address, it's not a channel. So in general, actors don't know who has their address. To do that would require some kind of synchronization. And busy actors can also update their state. And this means, for example, removing references from their local state. And notice that the parent can forget a reference before the message is even delivered. And finally, most popular actor languages allow actors to perform some kind of effect, like writing to a file. And once a busy actor has done everything that it wants to do, it can become idle again, ready to receive another message. One last piece of terminology I want to introduce is the concept of an unblocked actor. That just means that either the actor is busy now or it has an undelivered message, meaning it'll be busy at some point in the future. In this configuration, the unblocked actors are A and B, highlighted in blue. So what does it mean for an actor to be garbage? The standard definition is that garbage actors can be destroyed without affecting the system's observable behavior. But garbage collectors usually don't have access to an actor's internal code, so we're forced to be a little bit conservative. If there's any possibility for an actor to become unblocked, then it's not safe to garbage collect it. And this is because when the actor becomes busy, it might perform effects like writing to a log file. Instead, we want actors that we can prove will remain blocked forever. So that means they're idle and are never going to receive a message. For historical reasons, we call these actors terminated. Honestly, at this point, I wish we'd picked a different name for them. But anyway, clearly these actors are never going to be used, so it's safe to garbage collect them. So that's all well and good, but how do you know when an actor is terminated? Let's look at some examples. So suppose that this is the state of the entire actor system here. Is the blue actor X terminated? Well, notice that it's idle and it has no undelivered messages, so it's blocked. And also no actor has a reference to it. And since actors can't get references to each other just out of thin air, it means that no actor could ever get a reference to X. So yes, X is terminated because it's blocked and no actor could ever send it a message. Note that this is a type of terminated actor that you could actually detect using something like distributed reference counting. How about this case? Well, now there's a terminated actor C with a reference to X, but notice that it's blocked and so are all the other actors that are connected to it. So X is still terminated because every actor that could potentially send it a message is also blocked. In this case, we can see that there's a path from busy actor A to X. And now we can tell that if X is terminated because A could send a message to B, B could send a message to C, which can then send a message to X. So maybe X is terminated when all the actors that can reach it are blocked. Well, unfortunately, life is not that easy. Consider the following example. So here we see that all the actors that can reach X are blocked, except now there's a message to another actor E containing a reference to X. And here X might not be terminated because when E gets the message, it'll be unblocked and it'll have a reference to X. So the moral of the story is that it's not enough to just look at each actor's local state. We need to also consider messages that are in flight. So let's formalize this. We say that A is potentially acquainted with B if either A has a reference to B or there's an undelivered message to A that contains a reference to B. Both of these situations can lead to a future configuration in which A has a reference to B. So in either of these cases, we say that A is one of B's potential inverse acquaintances. And now we define potential reachability as the reflexive transitive closure of the potential acquaintance relation. Basically, when A can potentially reach D, it means that there's a path from A to D at some point in the future, once all these messages have been delivered. So you can see now that the problem with the last case was that even though X is only reachable by blocked actors, it's potentially reachable by an unblocked actor, namely E. In general, an actor might not be terminated if it's potentially reachable by some unblocked actor. So what if an actor is not potentially reachable by an unblocked actor? Well, then the actor is certainly terminated because at no point in the future could it possibly receive a message. So after all that work, we finally defined our problem. We're looking for the actors that are potentially reachable by blocked actors. So the question is, how do you find them? So one way you could find these terminated actors is to compute a global snapshot using an algorithm like Shandy-Lamport. But actually it's not as easy as it sounds because that algorithm doesn't support dynamic topologies like actor systems. But more fundamentally, that approach doesn't scale because one slow node prevents all the rest from being able to find any garbage at all. So there's a clever workaround in the Salsa GC, which uses approximate global snapshots, which are cheaper to compute and actually allows nodes to collect some local garbage. But their approach still has some pretty high overhead in practice. So each GC phase still significantly affects the application's performance. Our approach is based on Pony's GC, which is this fast message-based algorithm for multi-core systems. Their main limitation is relying on causal message delivery, which is expensive to implement in clusters. And we found a way to remove that requirement, making their approach scale. So how do these algorithms work, ours and Pony's, if they don't take a global snapshot? So here we see a demo. First, we need to make sure that all the actors communicate according to the special low overhead communication protocol that we've devised. Pony does the same thing, but using weighted reference counting. Either way, the protocol enriches each actor's state with this additional GC information that we call its knowledge set. And then whenever an actor suspects that it's become garbage, it takes a snapshot of its local state and sends it to a special actor called the snapshot aggregator. In Pony, actors have to do this whenever their message queue becomes empty. In our approach, actors can actually take snapshots whenever they want. And if you want, you could give each actor a different heuristic. So the snapshot aggregator collects these snapshots and periodically scans through them to look for actors that appear to be garbage. The magic of our approach is that even though these actors are taking snapshots with no coordination at all, we can still identify which of those snapshots are consistent with one another. When an aggregator discovers some garbage actors, it can just send it a self-destruct message to garbage collected. Now in Pony, this aggregator is a centralized entity, making it a bottleneck. But in our approach, you can actually have, for example, a snapshot aggregator at each node. And then you can have these aggregators disseminate their snapshots amongst themselves. So how can the snapshot aggregator tell whether an actor is terminated? Well, let's break it down. So first, the aggregator needs the ability to find any actor's potential inverse acquaintances. Then it can find the potential inverse acquaintances of those potential inverse acquaintances and so on, and that lets it find all the actors that can potentially reach a given actor. Secondly, we need to know whether all those actors can potentially reach it are blocked. Basically, that reduces to finding out whether an actor has any undelivered messages. Finally, and most intimidatingly, it needs to know which snapshots are consistent with one another despite being taken at these different times. So we address the first part with a kind of distributed contact tracing. Initially, we make sure that each actor knows the actor that spawned it, and then we make sure actors keep track of the references they send to each other. This lets you trace a path from one actor to all of its potential inverse acquaintances. This also lets us solve the second problem pretty easily, just by having actors keep count of how many messages they send and receive for each reference. And all this information is stored in that actor's local state and gets sent over to the snapshot aggregator whenever it takes a snapshot. But the burning question is, how can we tell if two snapshots are mutually consistent if they were taken at these different times? The answer is magic. And it turns out that the combination of contact tracing and message counts guarantees for us that any set of snapshots that appears to be terminated will also be consistent. So how do we do this contact tracing? First, we need to make a little modification. Instead of using these ordinary references, which are just addresses, remember, we ask the programmer to use these special reference objects that we call refobs. And a refob is just a triple that we denote x, a, lollipop, b, and where x is this globally unique token and a and b are actor addresses. So this refob can only be used by A, which is called its owner, to send messages to B, which is called the target. And when A is done with the refob, the programmer needs to deactivate it, which triggers a special protocol between A and B. So if refobs can only be used by their owners, how do you get new ones? So there's two ways. The first way is that the parent actor gets one whenever it spawns a child. And secondly, if A has refobs to B and C, then it can make a new one pointing from C to B. And let's see an example how this works. So here we have a busy actor A. The speech bubble shows its knowledge set, which remember holds some special GC related information. For simplicity, we represent this knowledge set as just a set of facts, kind of like in data log, but in practice you'd use something more optimized, some more optimized data structure. When A spawns an actor B, it gets a refob pointing to it, and this is represented by this active fact shown here. And similarly, when B is spawned, its knowledge set contains a fact saying that it knows this refob X has been created. To save space, I'm going to omit the additional information and just write X when we refer to the entire refob. So next, A spawns another actor C, which creates a refob Y. And now, suppose that A wants to give C a reference to B. To do that, it creates this new refob Z, sends it in the message, and it also adds this fact to say that A created a new refob Z using X. So notice at this point that C is a potential inverse acquaintance of B because of this message. But notice now that these knowledge sets create a path. B knows about X, which points to A knows about Z, which points to C. So this still holds even when C receives the message, causing it to add this fact to say that Z is active. So now, if A creates a lot of these refobs, then its knowledge set will keep growing without bound. So we give it a mechanism to forward the information to B inside of an info message. And analogously, when C decides it doesn't need Z anymore, it deactivates it. And that means it removes the fact about Z from its knowledge set and sends a release message to B. So now there are two ways this can go down, depending on which message gets received first. In this first case, the info message arrives first, and this causes B to add this fact to say there's a refob Z pointing to me, and I think it might still be in use. So notice now that there's a path directly from B to C instead of a path from B to A to C. And when B finally gets the release message, it can delete this fact. So in case 2, the release message arrives first, and this makes B add this fact to say, oh, I got a release message for Z, but I'm still waiting on that info message. And when it finally gets the message, it can delete the fact. The takeaway is that by looking at all these actors' states, we can figure out all of B's potential inverse acquaintances, unless there's an info message or a release message in transit. And more on that later. So let's look at message counts now, and these are pretty simple. Each actor just keeps track of how many messages it sent and received using each refob. And let's see this example. So here we have A getting a new refob that points to B. And when A uses the refob for the first time, it initializes the send count for that refob to 1. And we also need to attach the token to the message so that when it's delivered, the recipient knows which receive count to increment. In this case, it's receiving a message for this refob for the first time, so it initializes its receive count for 1 to 1. So the send and receive counts also need to be incremented whenever an info message is sent and received. And when an actor deactivates its refob, it deletes the send count, and when the target receives the release message, it deletes the receive count. Pretty simple. So, putting these pieces together, how do we tell whether an actor is terminated just by looking at these snapshots? So first remember that an actor is terminated if it's blocked, all of its potential inverse acquaintances are blocked, and so on. So let's say we have a set of snapshots S, and that actor B is the first one to take a snapshot. In the paper we prove that if B's knowledge set doesn't have any facts of the form created X, then actually has no potential inverse acquaintances and no undelivered messages. These actors are trivially terminated, and they can garbage collect themselves, actually. So what if it does have this created fact? That means A might be a potential inverse acquaintance of B. So to find out if B is terminated, we need a snapshot from A. And looking at A's snapshot, there's a couple possibilities. First, what if A's snapshot doesn't contain active X? So one possibility is that A hasn't received X from whoever created it. But that means that A is unblocked, which means that B is not terminated. Another possibility is that A sent a release message to B, but then B is unblocked because it has this undelivered message, so B is still not terminated. So basically, the aggregator knows that B is only terminated when A's snapshot contains active X. The second thing is that what if their message counts are not equal? Remember that we assumed that B's snapshot came first, so A's snapshot came after. And that means that A's send count can only be greater than B's receive count, which means that at some point after B took a snapshot, B became unblocked because A sent it a message. So the aggregator knows that B is only terminated if the message counts are equal. And moreover, we also know that no messages were sent along X between the time of A and B's snapshots. So here's the interesting bit. Suppose that A created a refob Y pointing to B before A took a snapshot. And remember that this causes it to add this created using fact to its knowledge set. And remember that the only way for A to forget this fact is by sending an info message to B. Could this have happened? Well, no. Because A would need to increment its sent count to send that message. But we assumed that the counts were equal, so any refobs that A created using X are guaranteed to be stored in A's knowledge set. And now the snapshot aggregator can see there is another actor potentially acquainted with B, so it needs a snapshot from that actor as well. And just like for A, if that snapshot contains active of Y, and its message count agrees with B, then it will also have any information about refobs that it created for B. So in this way, we can find every actor that's potentially acquainted with B, and we also learn that they haven't sent it any messages. So B is blocked, and in fact, it's actually been blocked ever since it took a snapshot. So what about the next actor to take a snapshot in S? Well, the proof that it's blocked too is pretty much the same, but now we use the assumption that the first actor B is already blocked. And so proceeding this way, we can conclude that every actor in S is blocked, so they're all terminated. So thanks for watching. Please feel free to email me if you want to talk or have any questions.